All right, well, let's get started. Kind of a small crowd. Maybe the distance from the location or something. Usually we get a lot more people showing up at 8 o'clock. Today you're gonna hear a fair amount about absolute quantification, and so I thought we would just do a hands-on exercise with absolute quantification. So if you go on your flash drive, there is an absolute quant folder. So
you need a flash drive.
So plug in your flash drive, and you want to grab this absolute quant folder. That looks better up there. And then just drag it to your documents. Actually, I probably have one I gotta get rid of. So it's inside data tutorials, and there's an absolute quant folder, and just drag it to your documents folder, and drag it to your documents folder so that it copies. And then you'll see it really actually only has raw files in it. So it's got a calibration curve and an unknown. So you can see that there's 8 standards files, and then there's this one Fox N1 GST, and that's the unknown. So let's, I'm gonna go, you don't necessarily need to do this, but I'm gonna go also to the Skyline website, and here is the absolute quant tutorial, and if I bring that up, then this is a written tutorial that you could go read through later, but the key part is this explanation here. Maybe I can make it a little bigger. So the experiment was a graduate student in our lab, Andrew Stragaci's, expressed. He was trying to measure transcription factors and really had no luck with them using DDA. And so what they did was they purchased a cDNA library from Josh LeVere at University of Arizona, and expressed all these transcription factor proteins, and then measured them in water, and then was able to measure them in endogenous samples after that using SRM. But when he expressed the proteins, he expressed them with the GST tag. So this is the DNA for the Fox N1 gene, and then there's a GST tag, and then in the GST tag there's a certain peptide that they found they could measure that was expressed well, and then he uses a calibration curve with an injected heavy peptide so that they could actually determine how much of the protein had been expressed. So we've got a sample with an unknown amount of protein in it, and we're gonna use the calibration curve and Skyline to determine how much of the protein is expressed. We've got a calibration curve with various concentrations, and an injected heavy peptide. We're gonna look at 2 ways. There's sort of 2 ways in the proteomics community that people, or not 2 ways, there are probably many ways, but there is a simple shorthand way that people use to calibrate, where they'll inject a heavy peptide and then just assume that if when the peak area of the endogenous is the same as the peak area of the heavy, then they must have the same amount in the sample, and then that also means that the peak area is half the peak area, and then they assume a slope of 1 and an intercept of 0, so if the peak area is half of what it is, and the peak area of the endogenous is half the heavy, then the assumption is that, oh, if you have very pure heavy, that it must be half as much endogenous. We're gonna test that theory out ourselves this morning by first doing the calibration that way, and then by doing the calibration using the entire calibration curve. All right, so in this case we don't. So I still have my IRT stuff up. I don't know if you have anything. If you don't have Skyline up, bring Skyline up. If you have Skyline up, just click New, and we're going to go through creating a completely new document. For this. So the first thing, let's just quickly go through the settings. We're going to turn on integrate all. Was integrate all explained yesterday? Okay, so we're going to turn on integrate all because we're doing a quantitative experiment. We want to integrate all in our document. And then we're going to go peptide settings. And in digestion, we don't really care about digestion because we're going to put in one peptide, but this is fine digestion. It's basically a triptych peptide. We're not going to have any retention time predictions, so you can just turn that off. The filtering is fine. We're going to have a 9 amino acid peptide. We don't need any library. And then in modifications, I guess I'm going to just use this top carbamide-methylcysteine or carbamide-methyl C. This is the old name of it, which must have been in the IRT document, but I'm going to use the modern naming. And then I guess from the IRT document, I had these two labels turned on. Does everybody have those two labels turned on? Yes or no? Okay, no. If you don't have them turned on, do you have them? Okay, so go ahead and just check them to make sure they're turned on. It's just the 15N N13C labeling of lysine and arginine. So that's a sort of standard SILAC type labeling. And that's all you need for now. Well, I guess let's go into quantification tab. We're going to normalize to ratio to heavy. So that's our normalization method in quantification. And we're not going to do a regression fit or weighting or anything, but we will say F mole is our units. And that's the same as you can see here. It's actually F mole. If we want, want to be exactly like this, we could call, this is just going to be a label, so we could call this per UL, right? Is that what it was? We've got per UL. Yeah, we'll get back to that, and we'll talk about 1 over x or 1 over x squared. But for at this point, no weighting, because we're not going to do the calibration curve yet. We're just going to try it without a calibration curve. We're going to see the answer we get, sort of take note of it, and then come back with a full calibration curve. But anyway, so we're just doing ratio. So this is the simple way to set things up if all you want is the assumption that when the endogenous and the heavy peptide produce the same peak area, they have the same concentration. And we'll see how well that holds. Okay, so let's just click OK. So we're done with the peptide settings. And then if we go to transition settings, we're not actually going to export a method. So over in prediction, we don't really care about declustering, we don't care about the various things we could, I'm going to leave it on Thermo TSQ Vantage for the collision energy. And then filtering, we want just charge 2. And I have P, so I want Y for the Y ions. So 2, 1, and Y. And then I want from ion 3, oops, 2, from ion 3 to the last ion. And then I don't need any special ions checked, and I'm not going to exclude anything around the precursor MZ. And that's good. And then I don't have a library, so that doesn't matter. The instrument settings are fine, and we're not doing, whoa, wild. I don't know why that's set up that way. I'm gonna just say no, there should be no full scan settings. Everybody there? Okay, so we have our settings all set up for this experiment. And now we're gonna go to edit, insert peptides. And we're gonna enter the peptide sequence that we're trying to measure, which is, let me see, can I get it? Yeah, so the goal is to get things looking like this. So the peptide sequence is sort of 3 triplets, IEA, IPQ, IDK. And the last one is IDK is actually a common acronym for I don't know. So IEA, IPQ, IDK. And I'm going to go enter that myself. IEA, IDQ, oops, is that IPQ, sorry. IPQ, IDK. So three triplets starting with IEA, IPQ, IDK. And then we're going to give it the protein name GST-tag. So does everybody have that? Okay, so then go and click insert. And now you'll have one peptide, and you'll see that you get 2 precursors, and we get Y3 through Y8, which is, so this is a 9 amino acid peptide, so the last Y ion is Y8. And let's see if this actually is explained here. Yeah, so here was a misconception we had that Andrew in his paper wrote that he did Y3 through Yn-1. So I said N-1 would be not Y8, right? Because there's N is 9 amino acids, so it would be 8. But somehow between Andrew and me, there was a confusion, and so Andrew thought that last ion -1 meant N-1. But but the last ion is N-1. So anyway, so we're going to find out that Andrew didn't actually measure all the way out to Y8. He measured out to Y7, but that was just a mistake. So in the future, I would encourage you to use the last ion, but we found in our lab that a lot of people were using N-1, which doesn't make much sense. So, but when we import the data, we'll see that we're going to be missing that ion. But that was just a confusion. Okay, so let's go ahead and import the data now. So we'll just go File, Import, Results. says we need to save the document, and so click OK to that. And you can go to your documents absolute quant folder where you should have no Sky files and just call this absolute. And then once you have saved it to absolute or whatever other name you like, we're going to do single injection replicates, and we're going to import those 9 replicates, those 9 raw files that are in this folder. Is everybody with me? Yeah, I saved it where I had my raw files, so I saved it into this absolute quant folder. So you can see I have absolute sky and absolute sky.view, and then these 9 raw files. Oh, I'm not working on for me it's in documents, but if you're working on your disk, then it's in data tutorials absolute quant. I don't really. Okay, so wherever you have it on the computer, you should have an absolute quant folder, and that's where you want to put it. I put it on my documents. Sometimes I was having people put it on the desktop, but it turns out that if you have a highly locked down computer, the desktop is controlled. So now I have already put it in their documents folder. Okay, so if you now click OK here, then you'll see these raw files and select them all. And I wish that I also have, sometimes I teach this with converted to MZML because raw files can load fairly slowly. So this might take a little bit of time to load. But my favorite way to select them all is just to drag a box around them. And then click OK. So this will now take a little bit of time to import. Yeah, but a bit longer time than if you. This is a nice thing about. I mean, I don't generally recommend that people convert their files, but if you're trying to teach people, it's a lot. The files import a lot more quickly if you've converted them to MZML. So yeah, this is just because of the way that Thermo stores their data. Sometimes it can be very slow. Yeah, and it's really their SRM, which they actually store as spectra, and so they have to extract chromatograms, and you can see that. Yep. It's exact. I mean, you'll just see WIF files. Skyline imports all of them. So, yep, doesn't. And it's even the same if you're using either Agilent or Waters. They store folders so that there's like .d and .raw folders instead of files. But when you go into that file import results UI, that's why that whole UI for importing results is like a custom UI. It's not a standard Windows open file dialog, and that allows us to make those folders appear like they're files. So, okay. So you can see, as I was, I'm gonna actually, I guess I'll hide this, and again. Does everybody remember how to get this back if you've hidden it? There's this button down in the bottom in the status bar that will bring the UI back at any time you want. And it seems to be going a little faster now. Maybe we'll get through this, but I'm going to hide it again. You can see that the Y8 was not measured. And I can just get rid of it by going Edit, Refine, Remove Missing Results. So Edit, Refine, Remove Missing Results, and that'll just get us the transitions that actually got measured. If I select down here and press F11, then I'm zoomed in and I can see here's my Fox end. This is my unknown here, and you can see the blue is the heavy. Whoops, I can turn on the legend. The blue is the heavy and the red is the light. And so I can get some initial sense of how close they are to each other. If I go to View, Peak Areas, Replicate Comparison, then I can see these as well. I can see side by side the light, and that the light is the red and the heavy is the blue. I can go View, Retention Times, Replicate Comparison, and now I get something showing me the retention times. So, okay, so while we're here, I guess I'll pull this out. This is probably the, so you know that there's five femtomoles of the heavy. What would you estimate there is of the light if you use the assumption that when they're equal, the heavy and the light are going to be equal, and there's basically a 1-to-1 slope. Yeah, so it might be 4 or high 3 or something like that. That's an estimate. That's one estimate. Okay, so then we can do one more thing, which is so let's go ahead and take a look at that. How Skyline basically will do that. Yeah. For retention time? For the replicate, this one, you have that? Yeah, so you just have to select the peptide itself. So this is a protein, and you'll get you'll get sort of every peptide in the protein. You'll see here's the little green thing showing you that's my peptide. But yeah, if you select the peptide itself, this is a useful view for us. I mean, we could also yesterday you learned, I mean, somebody might be in this mode where there's transition split graph, where you see everything sort of split up like this. But that we're really kind of interested in the relative, so I'm going to turn that back off because we're interested in how they look relative to each other. But let's go ahead and just quickly see. We're going to start using the document grid, where we can get numeric values. We can get all kinds of values for. I mentioned it in my presentation. Have you guys used it yet with Lindsay or anything? Document grid. Okay. Well, we're going to use it now. It's extremely useful. There's the document grid and the results grid are both useful ways of getting at information that's being graphed here. If you want to get at it numerically, it's very useful for exporting that information, and then you can plot it in Excel or R or whatever, and you're going to start using that more and more. Okay, so if you bring up the document grid, so yeah, you probably came up with this like proteins, and it says GST. That's fine. So what we're going to do actually is the first place we're going to go is, so you can see, you'll have these, everybody has these 5. These are just the standard 5 proteins, peptides, precursors, transitions, and replicates, and we'll deal with those in a second. But the first place we'll just go to is peptide quantification. So this gives us a chance to set something. And the thing that we're interested in right now is setting the internal standard concentration. Does anybody remember what the internal standard concentration was? 5 femtomoles. And so since we've got our unit set to 5 femtomoles, we can just type in 5 here. And let's take a look at this calibration curve thing. So there's a link out here that says calibration curve, and it's now telling me that it's got a slope of a slope of 20. I'm not even quite sure how it calculates that because we haven't really told it to make a calibration curve for us, but let's quickly take a look at that. So yeah, I guess it's plotted everything. These are all they're all plotted as x's, meaning they're unknowns. And wow, actually, it tells us what it thinks the calculated concentration of our unknown is 3.5387, so a little bit less than 4, but around that range, as we said. I can click on any one of these other ones and it will give me an estimate of its concentration. And this is all, again, just based on the ratio, right? So it's just doing that. It's assuming a slope of 1, and it's using this ratio and the fact that we set things to 5. So it doesn't actually have a calibration curve, but it gives us some information. I'm going to close that back down for the moment. Now, if we want to see that information numerically, then we can go to peptide ratio results. And now you can see all of these. You probably don't have this quite set up the way I have it. So I've already done this tutorial once, so I'm going to just go ahead and hide the. I think you don't have accuracy or analyte concentration. Does your graph look like, or your grid look like this? Okay. No? What does it look like? No, you got to go to View Peptide Ratio Results. One down from Peptide Quantification, Peptide Ratio Results. And then you have all these values, and this is now your quantification estimates for all of these things. Yeah, I think it's probably okay. One thing we can do is check. We could check order by acquired time, and that doesn't change anything. The other thing is we can switch. We can switch to value all, and then yeah, I don't know. That looks like fairly big retention time drift to me. Yeah, so I don't know why, but yeah, it doesn't really look like he had great control of his retention time, but I don't know how. If you wanted to, yeah, it's kind of weird that that's the acquired time order. I'm a little suspicious of that because it's sort of the reverse of the way a calibration curve would normally be acquired, right? Most concentrated one first. I don't know. Yeah, I had never noticed that before. But you might, So let's go enter the true concentrations, okay? So we'll go to views, replicates. So we know, they're not all unknowns. We know some of them, right? So let's go to views, replicates. And now we want to say that all the standards are standards. So you can see sample type. So we'll leave the top one unknown and we'll just set the next one as a standard and then press enter just to do that. And then rather than entering all 8 of them, which wouldn't be too much work, you can then click on the first one and drag to select and then right click and fill down. So that's the way I would get all those 8 set to standards is what? It's in views replicates. So views replicates, and then set the first one to standard, press enter, and then drag down and fill and right click fill down. So that's should bring us all here. And then now we need to get the concentrations, which we're all up on this page here. Unless somebody knows them by heart. Did anybody memorize them? So it's 40, yeah, 0.1 to 40, but it's a little bit 40, 12.5, 5, 2.5, 1. So really the 40, 12.5, 2.5, 1, 0.5, point. Oh my God, I'm off. Darn. Oh, I missed 5. 5, 2.5, 1, 0.5, 0.25, 0.1. So you just enter those in, you just type the numbers and then hit enter after each one. And that's how you would fill all those in. Does everybody have that? Anybody need more time to fill those in? All right, so then if we now switch our view back to the peptide ratio results view, we're going to customize it because I can pretty easily remember that the highest concentration is 40, and wow, it's 107 is not a great estimate. But I'd like to have those numbers closer together, so I'm going to go to Views, Edit View. And I'm going to, under Replicates, I'm going to add the analyte, this is the analyte concentration. So now I can see right next to the quantification, I can see the analyte concentration. So just under replicates, so you get into the customized view, under replicates, check analyte concentration. People have that? Thanks. Anybody need more time? Okay, so double click quantification, and then we'll show it in the column chooser. And then if you expand it, you can see that there's an accuracy. And that's only going to work if I have set analyte concentrations, but add accuracy as well. If you don't like where it shows up, you can move it by using these arrows. So I'm going to put it at the end, quantification, analyte concentration, and accuracy. So this gives me will give me a much better ability to sort of eyeball things. So I'm going to click OK. Does everybody have that? Not yet. Okay. So you want quantification at the end of this the columns. You want quantification, analyte, concentration, accuracy. Accuracy you just get by double clicking quantification. What? You just double click it, and just double click the column over here on the right side. If you double click the column on the right side, it will select it on the left side.
I'm assuming that I haven't entered the concentration of the internal standard.
Yeah.
Do you know where I can do that?
Yeah. So okay. So I'm gonna OK here, and then yeah, you should get actual values. And if you didn't, then you would go to peptide quantification, and you have to set internal standard concentration. And then, oh, you could enter it here, yeah. Yeah. So I could say, oh no, that's 100. I mean, you can edit it wherever you want. Yeah. So I guess yeah, we could have shortcut, but I wanted to go there and show the standard type too. So yeah, so now you can see that the accuracy is like 206. I mean, the accuracies are huge, and actually not a single accuracy. One of the labs we work with to define all this UI, and we work with quite closely, is the Duke lab. They're going to be putting on a week-long course at Duke this fall. It's Arthur Mosley's lab, and they say that they won't accept a point that's more than 15% either way, 85 to 115. So none of these points sort of meet the criteria of estimates within 15%. Oh, I don't know. Yeah, you cannot. All I heard was 15, so I don't. Maybe the lowest standard they allowed 20. Yeah, if we have time, we'll see, or otherwise I'll talk to you about it in a second. But yeah, there are some things once we start using a calibration curve that we're going to look at. So is everybody here? I guess there are now more and more people who are not actually following along. So okay, so we have this thing. We have our estimate of 3.5, but probably we're getting a little bit dubious about it, and you can get a sense also for why we should be dubious about it by so I just docked my grid at the bottom so that I can show you the curves as well. So we were estimating this as 3.5 or 4 based on how closely it matched the heavy, and that was based on the assumption that when the concentrations were equal, that these curves would be very equal. And so how could we check that? How do we check that assumption other than what we've just done? Because we actually have a point here where the standard 3 is 5 femtomole and the heavy peptide's 5 femtomole. So we can just go look at standard 3, because we're saying that we're basing our concentration estimates on this idea that when they're equal, they have very similar areas. So you can take a look. Oh, wait a second. When they're equal, there's lots more of the analyte than the standard. So somehow we're losing standard in this process. And then if you go look at analyte 4, wow, that's really pretty close. And I guess it kind of looks of the standards, it looks the closest to the GST, but the GST actually, our unknown is actually less than this. So now, what was standard 4? It's 2.5 femtomole. So if you were going to estimate now what would you estimate? So we're down from 4 to 3.5 to, okay, well it's less than standard 4. 4 only has 2.5, so what's your guess? Maybe 2, right? It's maybe a little bit less, or it's certainly closer to 2 than to 4. Okay, so let's go. That's what we'd like to do. Now I'm just sort of showing you, saying imagine where this is going to be based on what you see in these other samples. Now we're going to go define a curve. Yeah. Sorry, what? The same scale? Where don't you have that? Oh, you mean like, so transition, you have like transitions split graph like this?
The third versus 10 to the 6th, like 500 10 to the third instead of like 5 each to the 5th or whatever.
Let me just look. Oh, okay. Well, so you can. It's not easy to do it as you're just tabbing around, but if we went view range graphs in a row, that's kind of not enough space. Okay, so there they all are, and they all have their own scales. If I right click and turn on synchronized zooming, does everybody have synchronized zooming turned on? Anyway, if you don't have synchronized zooming on, check it. And then also you have to auto scale and turn off auto scale y-axis. So if you have synchronized zooming and auto scale at y-axis off, then we could go to our most concentrated one and just kind of scroll slightly. And then you would get, and now actually, because of the retention time shifts, some of them have shifted off the screen, but you can get now the y-axes are all exactly the same. Right, so that's one way. Synchronized zooming is one way to get your y-axes all the same. And I'm going to go back to Arrange Graphs tabbed, and I will just change my selection to get back to auto scaling the y-axis. All right, so let's actually do this calibration curve thing because we only have 10 minutes left. So we just go to settings, peptide settings, quantification, and we're going to do a linear regression. And we're going to leave no special weighting for the moment, but we'll come back and look at what happens if we change the weighting. Okay? So click OK. And then you should see quite a bit of change in accuracy. Right? Now we have 100% accuracy at the high concentration, very close to 100%. Actually, this 2.5 goes to 82%, which is a little bit low for, you know, that doesn't quite make our 15% cutoff. And then the lowest concentrations don't make our 15% cutoff at all. And that gives us some insight into the fact that we actually expect a lower limit of detection. So we expect the points to sort of, you know, once we hit the lower limit of detection, the points will curve. And they will stop being, it will stop having linearity. So let's go look at that by, you can just click on one of these quantification values, which will bring up the calibration curves. And it looks nice and linear up here. But if we, if you just click and drag a box down at the low end, you can sort of see that these last 3 points don't really follow this line, right? Everybody see that? Okay, so then one thing we could try is, so linear regression generally, you know, if you have a normal weighting for linear regression, then it's going to overweight the really high concentrations. So they're going to provide most of the weight. So what we might go try is settings, peptide settings, and now we could set the regression weighting to 1 over x squared, which is another commonly used value. And if you click OK, well, now you can see that the lowest concentrations come in within 15%, but we lose a lot of the upper concentrations. There's still some that come in within 15%, but our highest concentration now is you know, so this just sort of helps us understand that we don't have a straight line, right? Because we're losing various points, and our 2 highest points are too far away from what we'd like to see. If I undo this, if you right click and undo all zoom and pan, you can see that the line, because of the weighting, is now not really coming in with our highest concentration. So I'm gonna just undo to undo the change to 1 over x squared. And then you can see that line snaps back once you undo. And so now the next thing, so okay, so what is our estimate for our unknown now? What's the concentration for the unknown? Anybody? Well, it's appearing in multiple places on my screen right now. Calculated concentration equals 1.85. That's because I have this Fox GST tab. That will change depending on which tab I have activated. You can see the little red arrowhead pointing at which one I have. But when I have the unknown, it shows me 1.85, and it also shows me 1.85 in the grid. So that's one estimate, but I think we're being pulled off by these lower estimates. But that's pretty close. We said based on the curves that we thought it was probably pretty close to 2, right? Because we saw it was kind of close to the 2.5. So now I'm going to zoom in, and I think my understanding from Will Thompson from the Mosley lab at Duke is that they would just right click on these points, because they're not, again, they're like 150, 200%, and even 500% at the very lowest. So they would just right click on them and exclude from quantification. So they're not, even now, let's see, at this point, yeah, so this is still too far off, and I'll exclude it from quantification. Now even the 1 is potentially too far off, but I wonder if I go back to settings, what happens if I go with yeah, so if I go with 1 over x squared weighting, then at the point that I've excluded the lowest 3, I now have everything within everything is within 15%. And now at this point, my estimate of my concentration is still pretty close. It was 1.85, now it's 1.93. So yeah, pretty close to 2, what we just sort of guessed. And that would be the way by my understanding that someone in a lab doing calibration curves would estimate the concentration at this point. Okay? So we're pretty far from what was our original estimate was 3.5, just using the really simple inject a standard at known concentration. All right? Yeah. You don't get this quantification? This calc? Oh, it's the quantification. Yeah, it's the link here. Yeah, these are the ratios to standards. Yeah. Okay. All good? Okay, so everybody can take a moment. We're gonna transition over to our first speaker of the morning. Thanks to the people who showed up early.